All right, 9.3, finishing out this subtopic with thin film interference. So this was the equation for diffraction. And now we have two equations, and both of these describe a thin film interference. So like that pretty rainbow pattern you see off of oil slicks, that's thin film interference. We'll go more to that. So constructive interference for thin film in this case now occurs. You have 2dn. This n is not the maximum or the order. This n is the refractive index. D is the depth of the film. N is the refractive index. You guys remember from topic 4.4, I believe. M is the order in this case. It's a whole integer multiple. M equals 0 would be the middle of the interference pattern. M equals 1, 2 would be the subsequent patterns that you see, plus a half. Now in this case, with constructive interference, the reason we have a half is because of phase change, and we'll get to that, times the wavelength of light. So that's the condition where you have constructive interference. And then destructive interference, because of the nature of phase changes, it's 2dn equals m, a whole integer multiple this time, of the wavelength lambda. Now again, topic 4.4, that's where we see like Snell's law, n1 over n2 is equal to sine 2 over sine 1, sine theta 2 over sine theta 1. But in the refractive index is equal to, it's a ratio of the speed of light in a vacuum, c, divided by the speed of light in a medium, v. This number will always be greater than 1 because the speed of light in a vacuum should be greater than the speed of light in water or through glass or plastic or whatever. So in the refractive index, unitless number equals c over v. So what is thin film interference? You have seen it before: soap bubbles, gasoline spills on water, iridescence, and insects and feathers are all examples of thin film interference, that pretty rainbow pattern that you see. So shiny. So before we can understand this interference, we need to understand how this interference works. And to do that, we need to see what happens to waves that reflect at a boundary. So we're going to use rope, a heavy rope, which is really dense, and then a light rope. So if we have a rope, part of it's heavy, thick, dense medium on the left side, light, less dense medium on the right, and you send a pulse down this rope. Where the medium changes, what you have is part of the wave gets transmitted into the light rope, but part of it gets reflected back, as shown. Note that when it was reflected, when the energy that was transmitted went back this way, it was in phase. So a peak above the plane went forward, and then a peak above the plane went back. And the transmitted had the same as the original phase, but notice that the amplitude was reduced in that animation. Part of the energy was transmitted through the less dense rope, and part of it was reflected. The speed is less in the heavy rope than it is in the light rope. This is a metaphor for what happens with light. Light has the highest speed when there's no medium, when you're in a vacuum, and the speed of light decreases as you put particles in the way of the light. It's the opposite of sound. Now what happens though if we first send the pulse through the less dense medium, through the thinner rope, and we try to transmit it into the thicker rope? Pulse is sent, and then did you see the reflected pulse? The reflected pulse was inverted. It was out of phase, but the transmitted part of the wave was still in phase. It was still above the horizon. So we can remark on the following three properties. 1, you need to write these down. If a wave enters a boundary from a medium where the wave speed is lower, it will reflect in phase. Or where the medium is denser. So if you're going from a dense medium to less dense, then the reflection is in phase. The wave is in phase upon reflection. If a wave enters a boundary from a medium where the wave speed is higher, it will reflect out of phase. So this would have a less dense medium. So if the wave is coming from something less dense into something more dense, the reflection is out of phase. In any case, the wave is always transmitted through the boundary in phase with the original pulse. So no matter what, part of it is transmitted and it has the same phase as the original pulse. Now in optics, when we talk about density, we use the index of refraction. So consider a thin film of thickness lowercase d. It's made of a transparent medium having an index of refraction lowercase n. That n describes like the density. Light having a wavelength lambda is normally incident on the film. So for thin film interference to occur, we have to make an assumption that the light is incident normally at some angle with respect to the 90-degree line. We show it as at a slight angle. We have to assume that the light is totally incident, but I'm showing you at a slight angle so you can clearly see reflection and refraction. Okay, so at the top surface, some of the light is reflected, and then some of it gets refracted. It passes through the medium. So please copy this. Some of that light gets reflected, some of it gets refracted. It passes through. So the red arrow shows the refracted part. The purple smaller arrow shows the reflection. But again, I know we have to draw it at an angle, so it's easier to draw, but you have to assume, because there will be questions on this, for thin film interference, the light is normal onto the surface, onto the normal to the plane, okay? At each subsequent surface, reflection and refraction occur. So in the bottom part of the material, some of the light gets refracted, it passes through, and some of it, though, gets reflected at that boundary also. So for thin film interference, we have reflection occurring on at least two boundaries. The speed of light in air, or really in a vacuum, is c, not in air. And the speed of light, it's close enough to c that a lot of people just say it's c, but okay. And the speed of light in the medium is v equals c over n, which is always less than c. So the velocity inside of any medium is always less than the velocity of light in a vacuum. At the top surface, the reflected ray is out of phase with the incident ray. You're going from a low density region here in air to a high density. This reflection, just like we saw with the rope, this is out of phase now. This is out of phase by pi with the original wave. Inside the film, the transmitted ray is still in phase with the incident ray. So the red part is still in phase with the original. And it gets reflected off of this boundary here where you're going from high to low. So at this boundary of reflection, there is no phase change when you go from high to low, so it's still in phase. So what you see in this is the phase is typically represented by lowercase phi or lowercase phi plus lambda. So the original phase is phi for the incoming ray, and the reflected ray at the top boundary is phase shifted by pi. It's been inverted. The lower ray, the refracted ray, has the same phase. It reflects at the boundary, keeps its phase, and is transmitted through the top surface, still with the same phase as the original. So inside Inside the film, the light has actually traveled a distance of 2 times d. That should make sense. The light traveled down and back up. The angle of incidence is actually 0 degrees from the normal line. And again, I stress that this angle has been exaggerated just to make it easy to see. Speed of light in the medium is c divided by n, and speed equals distance over time. We see that inside the medium, the time for a typical crest to make it through the medium is 2dn over c with some substitution. Outside the medium, a crest travels m wavelengths lambda in the same amount of time. So m lambda over c for the time taken for the ray to be reflected at the top. You don't need to know that derivation, but it's helpful. So what we see is because the light in ray A and ray B are half a wavelength out of phase, when the two rays rejoin at the top, they will destructively interfere if their transit times are equal. So we get this equation for thin film destructive interference, but note this is true. You have 2dn is equal to m lambda. You have to assume a phase change at some boundary. This is true with a phase change at some boundary. If there is no phase change at either boundary, then of course you have to add a half wavelength. Similarly, it can be deduced that if we have a phase change at any boundary, at least a phase change somewhere, the rejoining rays will constructively interfere, and this can be defined with this equation. 2dn is equal to m plus a half times lambda. So these formulas are derived assuming the observer is on the same side as the light source, so the same side of the medium, that's where the same side of the incoming light, that's where you're standing. The formulas are derived assuming that only one of the rays was reflected pi out of phase, but at least one of them needs to be reflected. If they're both reflected pi out of phase, then you need to reverse the formulas. And these formulas assume the light is normal, light is normally incident. So we're here at our one practice problem for this set. A thin film of oil of constant thickness floats on the surface of water. The refractive indices of each material is shown on the diagram. When white light is normally incident on the surface of the oil, the film appears green to an observer. The wavelength of green light in air is 520 nanometers. Calculate the thickness of the oil. So we have white light, it is incident on a boundary, and it's going from a low index of refraction, a low density medium, to a high index of refraction, high density medium. So some of that light gets reflected and it undergoes a pi phase shift. The rest of the light gets refracted, passes through. Where it strikes a second boundary, it goes from a high index of refraction, a high density, to a low index of refraction, a low density medium. So no phase change occurs upon reflection here at this lower boundary. And then it refracts through the top layer. So these have a phase shift between these two rays. The phase difference is pi, they're out of phase by pi. The reason the observer sees green light is because of constructive interference. And so we can use the equation for constructive interference of a thin film, assuming at least one of the, at most one of the rays goes through a phase shift. It has to be one. There has to be a phase shift to use the equation like this, but for constructive interference, 2dn is equal to m plus 1/2 times lambda. And we're going to solve for the lowercase d. And we will assume that the person is seeing this m value, this m, as 0. So we'll just go with the first light that the person can see, the first pattern that would be present. So this equation becomes 2dn is equal to lambda over 2. And if we solve for D, we're going to use the index of refraction for oil. In this case, all of the refraction is occurring inside the oil. The oil is acting as our thin film. So we use this index of refraction in the equation. D is equal to lambda over 4 times, D is equal to lambda over 4 times N. 4N is in the bottom. So the width of the thin film, this value for D, in this case is, so the oil is really, really thin. It's 9.29 E negative 8 meters thick. Very, very thin amount of oil. All right, guys, thanks for watching. If you want more example problems, go to 9.3.3 in Cognity, I think, thin film interference. Good luck, study well.